What we want to do now is examine some of the features of titration curves. One of our goals will be to enable you to recognize what kind of titration is occurring based on the shape of the curve. So as we go through these different titration curves, look at the shape of that curve and try and associate the different points on that titration curve with what chemical species is in solution. Now, the first titration curve that we looked at was a strong acid, strong base titration. And the strong acid we were using was hydrochloric acid, and it was a 1 molar concentration, and I believe we had 100 mils of hydrochloric acid. And then the strong base that we were using was sodium hydroxide. It was also a 1 molar concentration. When you add a strong base to a strong acid or a strong acid to a strong base, you get a neutral salt and water. So the first point in the titration occurred before we had actually ever done any of the titration. So we just took the negative log of the hydrogen ion concentration from nothing but the strong acid. That was to give us a starting place, to see where we were starting with regard to the pH of our solution. So we had 0 milliliters of sodium hydroxide. It was a 1 molar concentration. We took the negative log of the 1 molar concentration and we got a 0 pH just from the excess hydrogen ion from the strong acid. Then we went ahead and we added 30 mils of our strong base sodium hydroxide. At that point in time, what happened was the hydroxide ion reacted with the hydrogen ion. Now, since we added 30 mils of 1 molar sodium hydroxide, that works out, volume times molarity, to be 0.03 moles of sodium hydroxide, and more importantly, just 0.03 moles of hydroxide ion. That means that 0.03 moles of hydrogen ion were consumed in that titration large K reaction. And we made 0.03 moles of sodium chloride and added a 0.03 moles of water to the solution. I did this in moles just now, but in the actual calculation we had to divide by the total solution volume to convert everything into molarity so that we could calculate the pH of the solution. The next thing we did was we added 100 mils of sodium hydroxide. It's of equal concentration, 1 molar. So since we had 100 mils of 1 molar sodium hydroxide, which is being added to 100 mils of 1 molar hydrochloric acid, that represented the equivalence point. Once we had divided by the total solution volume of 200 mils, that got us to a concentration of 0.5 molar for both the HCl and the sodium hydroxide. They completely consumed each other. And at that point in the titration where the strong base completely consumes the strong acid and there's no more strong base left, we call that the equivalence point, where we have stoichiometrically equivalent amounts of both acid and base. And at that point, since it's a strong acid and strong base, our only products are a neutral salt and water, and the pH was 7. The hydrogen ion and hydroxide ion concentration are equal to each other just from the autoionization of water. And then one more milliliter of sodium hydroxide, and all of a sudden the pH spikes because we have not only consumed all of the hydrochloric acid, we have an excess of hydroxide ion from our strong base. So we take the negative log of the hydroxide, get the POH, subtract it from 14 to get a pH of 11.697. Now I want you to notice the shape of a strong acid, strong base titration curve. We start low, have a pH of 7 at the equivalence point, and we end high with a high pH. Here is another representation without the values. As you can see, we're not at 0, so this is not exactly the same concentration. This is a 0.1 molar concentration of HCl. How can I tell that? Because the pH is approximately 1 here. The negative log of 0.1 is 1. And that's how I can tell that the strong acid HCl is a 0.1 molar concentration. We start adding strong base. The pH stays low because we have excess strong acid, but the concentration is getting lower and lower. As we get to the equivalence point, that is equivalent amounts, equivalent numbers of moles of sodium hydroxide and hydrochloric acid, we get to a pH of 7. It's only going to have a pH of 7 in a titration of either a strong acid, strong base, or strong base, strong acid. And then one more drop and we get a high pH. So take a look one more time at a strong acid, strong base titration curve. All right, let's take a look at a weak acid, strong base titration curve. We did the calculation for one of those as well. We chose acetic acid to be titrated with the strong base sodium hydroxide. Acetic acid is a weak acid. Again, we had a 1 molar concentration of acetic acid and a 1 molar concentration of sodium hydroxide. Initially, we had not added any sodium hydroxide to our weak acid, acetic acid. We simply did the ionization of the weak acid, developed our Ka expression. You remember that. It's Ka is equal to x squared over the initial concentration, which was 1 molar, and we came up with a pH of somewhere in the neighborhood of 2.7. And then we started adding sodium hydroxide. As we added sodium hydroxide, the sodium hydroxide reacted with the proton in acetic acid in a big K all the way reaction. This is still a big K reaction. Why? Because of the strong base. The strong base completely rips apart the hydrogen from the acetate ion, making our basic salt sodium acetate and some water. After 30 mils, we had a pH that equaled to 4.377. And this feature of a weak acid strong base curve is this long sloping region which we call the buffer region. This is where we have still some weak acid, but we've also made some of the conjugate base acetate in our solution. And then we got to the equivalence point. Now what I want you to remember at the equivalence point of titrating a weak acid with a strong base is that there is no weak acid left and there is no sodium hydroxide strong base left. All we have is a basic salt, and this basic salt makes the solution basic. That is, it creates a hydroxide ion concentration at the equivalence point that is not equal to the hydrogen ion concentration. It is above the hydrogen ion concentration. And so at the equivalence point of a weak acid being titrated with a strong base, we have a basic solution. And then we added one more drop of sodium hydroxide, and then we had excess hydroxide ion, and we got the pH simply from taking the negative log of the excess, not worrying about the weak base, which doesn't contribute to the basicity of the solution at that point. Now we want to take a look at the features and the shape of this weak base strong acid concentration. It starts out moderately low, but not extraordinarily low, somewhere in the neighborhood of 2.7, somewhere in that neighborhood. We start titrating it. Here's the buffer region. Why is it the buffer region? It's the buffer region because I still have weak acid in the same solution with a substantial amount of its conjugate base. The sodium hydroxide is converting the weak acid, acetic acid, to conjugate base, but I still have some weak acid left. Now, there is a particular point in the buffer region of every weak acid strong base curve, which we call the 1/2 equivalence point, where I have an absolutely equal concentration of weak acid as I do conjugate base salt, in this case HA and A minus. And then I can look over at the pH of the solution at the 1/2 equivalence point, and what I see is that pH is equal to pKa. I get that, or I can get that, from the Henderson-Hasselbalch equation. If A minus is equal to HA in concentration, then they cancel out each other, or they equal 1. If I take the same concentration over the same concentration, that equals 1. The log of 1 is 0, and the pH simply equals the pKa. So that's the 1/2 equivalence point where pH is equal to pKa. Now let's go to the equivalence point of the weak acid strong base titration. At the equivalence point, I've used up all my weak acid. I don't have any excess strong base. All I have is my basic salt, and that I've represented it as A-. So this solution will be basic at the equivalence point. And then one more drop, and I get excess hydroxide ion from the strong base, and my pH spikes very high. Let's take a look at the pKa dependence of different weak acid curves. If I draw a line through the 1/2 equivalence point in each case, and I'm trying to select a buffer solution, the way to do that is to look at that 1/2 equivalence point, and at the 1/2 equivalence point in each case for weak acids, the pH will equal the pKa. So if I need a buffer of somewhere in the neighborhood of 4 or 3.8, I would look at a weak acid that had a Ka of around 5 × 10 to the -4, and it's going to give me a pH somewhere in the neighborhood, well, actually it looks like around 5. And that is from the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of A- over HA, the base over the acid. And if I simply have HA is equal to A-, which I do at the 1/2 equivalence point, then pH simply equals pKa. And so we start out with a very high pH. We begin to add hydrochloric acid. The hydrogen ion reacts with the hydroxide ion to form water, and we get a neutral salt that's in solution. And so the pH stays high because we still have excess strong base. As we near the equivalence point, all of a sudden we add equal amounts of hydrochloric acid to sodium hydroxide, and at the equivalence point we wind up with just sodium chloride and some water. It's a neutral salt, so the pH is 7. And then one more drop of HCl, and the pH plummets down to very low pHs that correspond to strong acids in excess. So take a look at the shape of a strong base being titrated with a strong acid. Since it's a weak base that we're starting with and we're titrating it with a strong acid, the pH starts out kind of high, certainly in the basic region, but not extraordinarily high. We begin to add our strong acid, but we don't add as much strong acid as we have weak base in solution. So as that's occurring, the H plus is binding to the conjugate base of our acid, or to the anion of our weak acid, and it's making that weak acid. We start out, we make a little bit more HA. Each time we add another mole of hydrochloric acid, we consume another mole of weak base, and we make another mole of weak acid. So in this part of the titration curve, we call that the buffer region, because I have a weak base concentration and I've made some weak acid. So this would be the buffer region of my weak base strong acid titration curve. At the equivalence point, I have no more HCl. I've added an equal amount, an equal number of moles of HCl as I have of weak base. So both of my reactants are gone. What do I have left? I have a weak acid concentration. And so since I have a weak acid concentration at the equivalence point, my solution is going to be below 7. It will be acidic at the equivalence point of a weak base being titrated with a strong acid. Once I get down here in the low part of the curve, I definitely have some weak acid, but more importantly, I have a concentration of strong acid, and if I wanted the pH, I would get the pH only from the excess strong acid. Similarly to getting the pH of a weak acid strong base concentration from the excess hydroxide, in a weak base strong acid titration, I get the pH only from the excess strong acid. Just to give you a look at a polyprotic acid titration, I believe you're going to do citric acid, which is a triprotic acid, in lab. What we have here is a number of Kas. We have a Ka for H3PO3. This is phosphorus acid. We also have a Ka, because this is a triprotic acid, we have a Ka for dihydrogen phosphite, and we have another Ka for hydrogen phosphite. So we have actually 3 Kas, and technically we should have 3 buffer regions. The other one is not represented on this curve. So we have 3 buffer regions. The first buffer region would be associated with H3PO3 and H2PO3, and if I needed a Ka to solve that buffer problem for the pH, I would use Ka1, take the negative log of that, and that would be pKa1. If I wanted to solve for this particular buffer region here, I would use the pKa for dihydrogen phosphite, because in this buffer region my acid is H2PO3 minus and my conjugate weak base is HPO3 2 minus. And then for the third buffer region up here, I would use Ka3, take the negative log of that to get pKa3. So that's a polyprotic acid, and that's what the curve looks like. Associate yourself with the different shapes of the curves.